Hi everyone, you are very welcome to week 2 of our NLP course. And this week is about very core NLP tasks. So we are going to speak about language models first, and then about some models that work with sequences of words. For example, part-of-speech tagging or named entity recognition. All those tasks are building blocks for NLP applications, and they're very, very useful. So first things first, let's start with language models. Imagine you see some beginning of a sentence, like this is the. How would you continue it? Probably as a human you know that this is house sounds nice, or this is did sounds not nice. You have some intuition. So how do you know this? Well, you have read some books, you have seen some texts, so that's obvious for you. Can we build similar intuition for computers? Well, we can try. So we can try to estimate probabilities of the next word given the previous words. But to do this, first of all, we need some data. So let us get some toy corpus. This is a nice toy corpus about the house that Jack built. And let us try to use it to estimate the probability of house given this is the. So there are 4 interesting fragments here, and only one of them is exactly what we need. This is the house. So it means that the probability will be 1 out of 4. By C here, I denote the counts, so this is the count of this is the house or any other pieces of text. And these pieces of texts are n-grams. N-gram is a sequence of n words, so we can speak about 4 grams here. We can also speak about unigrams, bigrams, trigrams, etc. And we can try to choose the best n, and we will speak about it later. But for now, what about bigrams? Can you imagine what happens for bigrams? For example, how to estimate probability of Jack given build? Okay, so we can count all different bigrams here, like that Jack, that lay, etc. and say that only 4 of them are that Jack. It means that the probability should be 4 divided by 10. So what's next? We can count some probabilities, we can estimate them from data. Why do we need this? How can we use this? Actually, we need this everywhere. So to begin with, let's discuss this smart reply technology. This is a technology by Google. You can get some email and it tries to suggest some automatic reply. So, for example, it can suggest that you should say thank you. How does this happen? Well, this is some text generation, right? This is some language model, and we will speak about this later in many, many details during week 4. So, also there are some other applications like machine translation or speech recognition. In all of these applications, you try to generate some text from some other data. It means that you want to evaluate probabilities of text, probabilities of long sequences. Like here, can we evaluate the probability of this is the house? Or the probability of a long, long sequence of 100 words? Well, it can be complicated because maybe the whole probability, the whole sequence never occurs in the data. So we can count something, but we need somehow to deal with small pieces of this sequence, right? So let's do some math to understand how to deal with small pieces of this sequence. So here, this is our sequence of k words, and we would like to estimate this probability, and we can apply chain rule, which means that we take the probability of the first word and then condition the next word on this word and so on. So that's already better. But what about this last term here? It's still kind of complicated because the prefix, the condition there, is too long. So can we get rid of it? Yes, we can. So actually, Markov assumption says you should not care about all the history. You should just forget it. You should just take the last n terms and condition on them. Or to be correct, last n-1 terms. So this is rather intuitive assumption because not everything in the text is connected, and it is definitely very helpful for us because now we have some chance to estimate these probabilities. So here, what happens for n equal 2 for bigger model? You can recognize that we already know how to estimate all those small probabilities in the right-hand side, which means we can solve our task. So for a toy corpus again, we can estimate the probabilities, and that's what we get. Is it clear for now? I hope it is, but I want you to think about if everything is nice here. Are we done? Well, I see at least two problems here. And I'm gonna describe both of them, and we will try to fix them. Actually, it's super easy to fix them. So first, let's look into the first word here, and the probability of this first word. So the first word can be this or that in our toy corpus, but it can never be mold or something else. Well, maybe we should use this, so maybe we should not spread the probability among all possible words in the vocabulary, but we should just stick to those that are likely to be in the first spot. And we can do this. Let us just condition our first word on a fake start token. So let's add this fake start token in the beginning, and then we will get the probability equal to 1/2 for the first place, right? Because we have either this or that. So it can be helpful. What else? Actually, there is another problem here. So how do you think, is this probability normalized across all different sequences of different length? Well, it's not good. So here we have the probabilities of short sequences, of the sequences of length 1, equal to 1, and then all the sequences of length 2 also sum into the probability equal to 1, but that's not what we wanted. We wanted to have one distribution over all sequences. First, I will show you how to fix that, like this, and then we will discuss why it helps. So let us add the fake token in the end, as we did in the beginning, and let us have this probability of the end token given the last term. Okay, easy. Now, why does that help? So imagine some generative process. Imagine how this model generates next words. I'm going to show you the example how it generates different sequences, and hopefully we will see that all the sequences will fall into one big probability mass. They will spread this probability mass among them. So this is some toy corpus again. We want to evaluate this probability, and this is untouched probability mass yet. Let's cut it. So we can go for dog or for cat. Let's go for cat. Now we can decide whether we want to go for tiger or for dog, or if we want to terminate. And this is super important. So now the model has an option to terminate. That's not what it could do without the fake end token. So this is the place where things would go wrong if we didn't add this fake token. So, okay, now we decide to pick something. We can split further and pick and split and pick. And this is exactly the probability of this sequence that we wanted to evaluate. But what's more important, you can imagine that you can also split all the other areas in different parts, and then all of them will fit into this area, right? So all the sequences of different lengths altogether will give the probability mass equal to 1, which means that it is correctly normalized probability. Congratulations! Here we are. So just to summarize, we could introduce big RAM language model that factorizes the probability into terms, and we could learn how to evaluate these terms just from data. So you can see two formulas here in the bottom of the slide, and let it a moment to see that they are the same. So when you normalize your count of n-grams, you can either think about it as counting n-1 grams, Or you can think about it as counting n-1 gram plus different continuations, all possible options, and sum over all those possible options. Okay, hope you could see that it is really about counting. And in the next videos, we will continue to study in more details how to train this model, how to test this model, and what other problems we have here. Thank you.